Let us begin the lesson on rational numbers. Have a look at these simple algebraic equations. The equation A is true for x equal to 1. We know 1 is a natural number. If we consider equation B, its solution is x equal to 0. So, we have to extend our reach to whole number set now. The equation C has its root -1. Now, we pick the solution from the set of integers. The last equation has no solution in the group of integers. We need fractions here. X equal to 3/4 makes it true. Thus, we realize the need for a larger group of numbers, and we here introduce rational number set. Look at the flow chart. The biggest set of numbers, that is rational numbers. Under that comes fractions, decimals, integers, and under integers whole number comes, and under whole numbers natural number comes. Under the decimals we have terminating decimals and repeating decimals. So the definition of rational numbers: a number a by b is a rational number if a and b are integers and b is not equal to 0. B cannot be equal to 0 because division by 0 is not defined. For example, 4/5 minus 10/9, etc. Rational numbers include all the natural numbers, whole numbers, integers, and all fractions, decimals, etc. as we have studied. Note that 0 is also a rational number because it can be written as 0/1, 0/2, 0/3, etc., etc., etc. How to write a rational number in a standard form? The rational number is said to be in the standard form if and only if the numerator and the denominator are co-prime. That is, they have no common factor other than 1. The denominator of a rational number is positive compulsorily. For example, the rational number 4/9 is in its standard form because both 4 and 9 are co-prime and the denominator 9 is positive. Let us check the difference between the simplest form and the standard form. Consider the number -75/30. The simplest form of this number is -5/2, as we divide 75 and 30 each by the HCF 15. Now, the simplest form we have written is -5/2, and the numerator is carrying the minus sign. It is a negative rational number. Is it in the standard form? No, because it is improper negative. Though the numerator alone is negative, we need to express it in the mixed form as -2 1/2. So, standard form is one more step ahead of the simplest form, where we check whether the numerator is negative if the rational number is negative. Consider the second example, -51 by -34, where the simplest form of this is 3/2. We divided it by 17, the HCF of 51 and 34. And the rational number is positive because both 51 and 34 were given negative. A division of two negative numbers gives us positive. So the simplest form is 3/2. But in the standard form, we expect the mixed form, that is 1 by 2. The third example, 57 by minus 38 is similarly 3 by minus 2 in the simplest form. But unless we put the minus sign in the numerator, it is only the simplest form, but the standard form expects minus 3 by 2 is equal to minus 1 by 2. So, it is important to note that no negative sign appears in the denominator of a rational number in the standard form. In the standard form, no further simplification is also possible. All simplest forms are not standard forms, but all the standard forms are in the simplest form. How to represent rational numbers on a number line? Like natural numbers and integers, rational numbers also can be represented on a number line. To express rational numbers appropriately on a number line, we have to divide each unit length into as many number of equal parts as the denominator of the rational number is. And we have to proceed as shown. Example, to express 7 by 3, minus 4 by 3, 2 by 3, minus 1 by 3, 8 by 3 on the number line. The steps are explained. Draw a line, mark each unit length from 0, 1, 2, 3, etc. to the right of the number line, to the right of 0, and minus 1, minus 2, minus 3 to the left. Divide each unit length into equal division as per the denominator. Now mark the required points at appropriate positions as done in the figure. There is an easy method to represent the rational numbers on a number line. You can see a number line where the vertical lines are the ruled lines in your page of the notebook. We can use this feature as these lines are equidistant. See, use the ruled page by turning it to 90 degree. Turn it to see the equidistant vertical lines and consider the page in the ulta manner. Now take any L-shaped object and draw a L shape to confirm the 90 degree. That is, it is parallel to the margin of your page. Along one edge of the L, draw a complete number line horizontally to cut the vertical lines in the page of the notebook. Mark points at equal distances. You no need to measure using the ruler, just mark the equal points using the lines in your notebook. Then mark integers on it. Mark all the integers as per the numerators of the numbers given. See, the example here is represent minus 2 by 9, minus 11 by 9, 1 by 9, minus 7 by 9, minus 4 by 9, 4 by 9, etc. on the number line. See how the page is used. It is turned by 90 degree and ensure that it is L shape is making it 90 degree, and then continue before marking the number line as well as the markings on the number line. So after you mark the integers, write the same denominator to all the numbers given, and finally you can replace the numbers minus 9 by 9 by minus 1. As we know, minus 9 by 9 is minus 1. Similarly, whichever integer part comes can be replaced by writing the integer very close to it. This is the easiest method instead of finding how many parts we have to divide in between the two rational numbers. Wow, this is a beautiful picture of a rational number line in the nature. Can it be number line of integers in the nature? Yes, Of course. See the equidistant trees, and I can see the symmetry also here. And the reflection symmetry, linear symmetry, what not. What are the applications of rational numbers in reality? The patterns in rational numbers are connected to nature and culture. The application of these patterns in scientific field, especially in computer programming, music, notes and internotes, poetry, stanza and syllables, can be explored. The following is a website which you can refer for exploring on the topic. There are two patterns on numbers, rational numbers, example 1 and example 2 shown here. They are the most widely used patterns in various fields, scientific fields. Now, coming to additive inverse. What is the common word which is used for additive inverse? That is opposite. The opposite of a number or the negative of a number is nothing but additive inverse. So consider a rational number 7 by 3. There exists a rational number minus 7 by 3 such that when I add 7 by 3 to minus 7 by 3, the result is 0. That is 7 by 3 plus minus 7 by 3 is equal to 0. Then this minus 7 by 3 is called the additive inverse of 7 by 3 or opposite of 7 by 3 or negative of 7 by 3 and vice versa. What does this vice versa mean? The additive inverse of minus 7 by 3 is nothing but 7 by 3. Every rational number has its additive inverse. For example, minus 8 by 9 has its additive inverse 8 by 9 such that minus 8 by 9 plus 8 by 9 is 0. What is this 0? It is the additive identity. Yes. So, there is a pattern in this. Any number plus its additive inverse gives additive identity. Therefore, we can write x plus minus x is equal to 0 or a by b plus minus a by b is equal to 0. The rational number which is equal to its negative is 0 because 0 is neither positive nor negative. So I cannot say that the negative of 0 is negative 0. There is nothing like that. The multiplicative inverse or the reciprocal. Consider any rational number, say 3 by 5. There exists a rational number which when multiplied by 3 by 5 will give the product 1. The number is 5 by 3. So if I multiply 5 by 3 to 3 by 5, the product would be multiplicative identity. So 3 by 5 is called the reciprocal of 5 by 3 and vice versa, or 5 by 3 is called the reciprocal of 3 by 5. For any rational number minus 5 by 8, say for example there exists minus 8 by 5 such that minus 5 by 8 into minus 8 by 5 is equal to 1. Here we need to remember that the multiplicative inverse has the same sign as the given number. The sign doesn't change. Only the numerator and the denominator get exchanged. We do write the position of these two in a inverted manner. 0 has no reciprocal because 1 by 0 does not exist. For rational numbers 1 and minus 1, the reciprocal is same as the number. In general, any number added to its additive inverse gives 0. which is the additive identity. Also, any number multiplied to its multiplicative inverse gives 1, the multiplicative identity. Generalized form of this can be written as a by b plus minus a by b is equal to 0, where a by b and minus a by b are mutually opposites. Also, a by b into b by a is equal to 1, where a by b and b by a are the reciprocals of each other. Two examples are provided for each. There are few examples for multiplicative inverse of the following, and we have to verify whether the answer we have written is a multiplicative inverse by multiplying and getting the answer multiplication, identity of multiplication. So that is done here. There are 5 to 6 examples. Absolute value of a rational number. The absolute value of a rational number is the number with no regard to its sign. So, any rational number, whether it is positive or negative, when the absolute value is taken, it just remains the number, no sign, positive or negative. So, absolute value of minus 2 by 5 is 2 by 5. Absolute value of 3 by minus 2 is 3 by 2, etc. What is applicable for integers here is exactly applicable for rational numbers. So, except 0, all the absolute values are positive. Because 0 has no sign, we cannot consider it as positive. It is 0. And we don't say positive. The reason is, it is the distance between 0 and the number on the number line. Therefore, without considering the direction, we are considering the distance from 0 to the number given. That is why it is called absolute value. Here are few operations on rational numbers which we have already studied. The addition and the subtraction involved here. When we add and subtract, we don't take cancellation process. We are doing LCM here, remember. So, we are keen on finding out what is the denominator given in the rational number when we add and subtract. So, accordingly, I have used certain colors to combine the rational numbers, which makes it easy to add. Say in the given first example, the denominators are 7 and 6. But it is easy if I try to do mentally, or if I want to do it faster, it is obviously if I combine the denominator 7, the two numbers, similarly which are the denominator 6, two numbers. So I have used the same color for those, and the operation which we have studied last year exactly used the same method, and we reached the answer to 1 by 21. So let us go through the steps. Minus 4 by 7 plus 2 by 7 is added, and that gives minus 2 by 7, as minus 4 plus 2 is minus 2. Similarly, 7 by 6 and minus 11 by 6 added, minus 4 by 6 is given, and finally we arrive at the LCM mandatory step, that is when we get 7 and 3 as denominators, we add it by taking the LCM. Otherwise, you imagine in the beginning, if we take LCM, it would be 42 and the numbers proportionately become bigger and make the process of solving complex. Consider the second example where 3 by 8, 7 by 2 and minus 3 by 5 and 3 other rational numbers with similar denominators are given. So here again I use the same process by combining the denominators which are like. So combining two rational numbers with similar denominators, it makes it very easy to calculate and we reach the answer faster. So such a method makes it easier to solve operation sums on rational numbers. Few more are here. Of course, these can be done using mental arithmetic method. See, we no need to use the regular procedure as we solve using pen and paper. Consider 7 1 by 5 minus 2 by 5. As 7 1 by 5 and 2 by 5 both have denominators 5, and 7 1 by 5 is a combination of 6 plus 1 by 5, and again in 1 1 by 5 there are 1 and 1 by 5, and 1 again is 4 by 5 and 1 by 5. So we need to visualize this fractional operation and just go through this operation pictorial representation 2-3 times. You can do such sums without converting this 7 1 by 5 into improper and taking LCM. You can do it faster. So the answer is 6 4 by 5. Similarly, there is one more example where 23 1 by 15 added to 6 17 by 30. So the answer would be 29 19 by 30. It is also a mental arithmetic sum. Next one is 13 5 by 12 and minus 7 by 12. Again, this can be done orally without pen and paper. So you can imagine that 1 can be written as same number by same number. It can be 23 by 23, 7 by 7, 15 by 15, 20 by 20, 88 by 88, etc. Simplify type of problems. Observe the first one carefully. Simplify the first one. First bracket you observe. Minus 7 and minus 7 gets cancelled. Because it is multiplication, it is cancellation. Minus 7 by 18 and 15 by minus 7 can be done in mind. Minus 7 cancels. 15 by 18 is 3 5s are 3 6s are. It is 5 by 6. Almost last but one step has that 5 by 6. But can you do it mentally? Yes, of course. 5 by 6 is the answer. Coming to the second bracket, it is 1 into 1 by 4. Quite easy. 1 into 1 by 4 is 1 by 4 and it is again there. And last one is half of quarter. It is 1 by 8. Multiplication, last bracket. So 3 brackets can be done in mind, and then you can directly write 5 by 6 minus 1 by 4 plus 1 by 8. Last but one step. Then the LCM 24, of course you need slight calculation, pen and paper may be needed, but otherwise you can directly come to the step 5 by 6 plus minus 1 by 4 plus 1 by 8. Next one also. First bracket you observe 2 1s are 2 2s are. Minus 3 by 2 multiplied to 4 by 5. You have to visualize 2 1s are 2 2s are, and then 2 gets multiplied to minus 3. So it is minus 6 by 5. And second bracket 5 1s are 5 2s are. So it is again 3 and 9 cancelled. So 3 and minus 2 gets multiplied, minus 6 by 1. Last one 3 by 8. So you can reach at the last but one step in both these sums quickly without much difficulty. But you need many more sums to be in hand, and then you have to try them out by writing first, and then when you see, you realize. That is called comfortable zone of solving. You will have less doubts and you will be more confident. Third problem, which is geometry based on area of the triangle. The problem says a perpendicular of a right angled triangle is 3 by 2 times of the base. 3 by 2 is 1.5. So it is 1.5 times the base. The base is shorter. It is 10 centimeter and the perpendicular is 1.5 times. 1.5 times 10 should be 15. We all know that. So that is calculated. So perpendicular is indirectly given. Base is directly given. After calculating the perpendicular as 15 centimeter, we go for substituting the values in the formula, which is learnt in the previous class as half into base into height. Before all this, it is very important that we note in a right angled triangle, the perpendicular is the altitude and the base is one of the side which meets the perpendicular where the 90 degree is formed. So the two sides which make 90 degree are themselves mutually base and the perpendicular, and the third longest side becomes the hypotenuse, and we have learnt that Pythagoras theorem is applicable for right angled triangle, and this concept has to be taken forward because perpendicular word and the base word often it is seen as in a right angled triangle. You have to identify. The data will not be given directly. It is given as, sometimes it will be given as the two sides which form a right angle. The relation between these two will be given. So the area of the right angled triangle is, after substitution in the formula, then cancellation, you get it as 75 square centimeter. First, let's recollect the equivalent rational numbers. Rational numbers that are equal to each other in their simplest forms are called equivalent rational numbers. Consider the example minus 18 by 24. When it is divided by 6, the HCF of 18 and 24, we get minus 3 by 4, which is the simplest form, also the standard form of the rational number. 14 by minus 21 gives 2 by minus 3 in the simplest form. It's not the standard form because the negative 3 is in the denominator. But it is to be noted that minus 18 by 24 and minus 3 by 4 are equivalent, and minus 14 by 21 or 14 by minus 21 equivalent to 2 by minus 3 or minus 2 by 3. Next example, minus 8 by 9, when multiplied with 3 each to numerator and denominator, we get minus 24 by 27. This is equivalent to minus 8 by 9. And we started with the simplest form and we reached at the higher order rational number. Consider the last example, minus 5 by minus 6, which is a positive rational, as both numerator and denominators are negative, they get cancelled and we get 5 by 6 as the rational number. And when I multiply by 4, say any random number, but both numerator and denominator when multiplied by 4, we get 20 by 24, which is the higher equivalent rational number. So in this case we have 4 pairs of equivalent rational numbers, and when two rational numbers are equivalent, note that they have the same sign and they are equal in their simplest form. Where do we use these equivalent rational numbers while solving sums? Let us just check. First, to understand the equivalent rational numbers better, here there is a representation of various rational numbers on the number line. We are already familiar with the representation. In the previous presentation it is taught, and this is one of the easier way to represent the rational numbers, and we have used the ruled page in the ulta manner, considering the lines to be equidistant. The central number line is the one which we considered as an example in the last class, and we have taken the denominator as 3. The number was having, the rational numbers were, all the numbers were having the denominator 3. So the number line has 0 at the center, 1 by 3, 2 by 3, 3 by 3, etc. on the right, and minus 1 by 3, minus 2 by 3, etc. on the left. Now, just the replica of the same number line is drawn above as well as below. So if you observe the number line which is above, it is now having double number of markings. So the middle marking which was not marked previously is now marked. So consider the another number line. Similarly, there also the number lines, each line which is there in the ruled page is used to mark various rational numbers. So consider the central number, the 0. It matches in all the 3. Go along the vertical line where 0 is there in all the 3 number lines. All the zeros are in the same vertical line. Move to the right of 0. The middle number line has nothing, and the top number line has 2 by 12, and the bottommost number line has 1 by 6. What does this mean? That 2 by 12 is equal to 1 by 6. So what is the missing one which is in the middle number line? Topmost has 2 by 12 and the bottommost has 1 by 6, and the middle one has 0 on the left and 1 by 3 on the right. It should be 0.5 by, you can just check, 0.5 by 3. So accordingly, if you consider various other number lines along the vertical line, consider that 1 by 3 in the middle number line. Go along the vertical line and you have 4 by 12 there. Aren't they equivalent? 1 by 3 is equal to 4 by 12. And if you come down, you have 2 by 6, again equivalent to 1 by 3. So along that vertical line, at the center 1 by 3, at the top 4 by 12, and at the bottommost 2 by 6. So if you consider various such combinations, all vertical lines having equivalent rational numbers tells us so many features of these rational numbers. So if you consider the top number line, the same distance previously which we used from minus 7 by 3 to 7 by 3 is now depicting minus 28 by 12 to up to 28 by 12. So 28 by 12 is equal to 7 by 3, and minus 28 by 12 is minus 7 by 3, and there are other numbers also in between. Only thing is the same distance is divided into 12 equal parts. Previously it was 3 equal parts. So it depends on how we divide the distance. Previously when we marked integers, we used to take it as 1, 0, minus 1, minus 2, likewise we used to mark. So depending on the availability, we use the page, and the same distance can have plenty of numbers. So again, if you go to divide, you will get, say, consider the topmost number line, minus 28 by 12 is there, minus 26 by 12 is there. What is in the middle? It is minus 27 by 12, which is not marked, but it is there at the middle. So we go to realize that in between two equal divisions, if we go to mark them and if we go to find them, there are many more rational numbers and they are all positionally equivalent. If at all, if such simultaneously many number lines are marked. Similarly, the bottommost number line, if you just observe, it has the denominator 6, that is, it is divided into, we considered 6, and the unmarked one is minus 13 by 6, which is written on the top, and then it is equivalent to minus 26 by 12 on the top number line. Minus 13 by 6 at the bottommost number line, move along the vertical line, you will get minus 26 by 12. So they are equivalents. What would be the central number line depicting there, which is between minus 7 by 3 and minus 6 by 3? It is nothing but minus 6 and half by 3. Minus 6 and half by 3. It is a decimal form, you may have to convert. So you are going to recreate this number line in your long notebook, and you have to illustrate how it is represented yourself. So if you have understood, look at these number lines once again and try to understand various concepts are there. We are going to use this once again when we come to the density property of the rational numbers, finding numerously many number lines, numbers in between the two numbers using certain methods. Here is the one where we previously just now we saw an example of equivalent forms of rational numbers. Where are we using them? Where do we find? So the best examples are shown here. When we add two rational numbers, say one negative or one positive or whichever, any two rational numbers in general, when we add, we take LCM. So you can observe minus 3 by 2 added to 5 by 7, LCM is 14. 2 and 7 are the denominators, LCM is 14. So minus 3 by 2 becomes minus 21 by 14. How is it? 2 sevens are 14, minus 3 sevens are minus 21. Similarly, 5 by 7, 7 twos are 14, 5 twos are 10. And when we add, we get minus 11 by 14. So it is important to note that minus 3 by 2 was the given rational number, and when I am adding it, I wrote the equivalent form of minus 21 by minus 3 by 2 as minus 21 by 14, and 5 by 7 was given. I wrote the equivalent form of 5 by 7 to add, and I wrote it as 10 by 14. So it means I didn't change the numbers given. By taking LCM, I wrote equal form of 5 by 7, but I took it as 10 by 14, so that it is easy to add. When the denominators are same, we can further move on to the addition process and then we add. It's already learnt. So simplest form was given or simpler form was given. We move to the higher order when we add. Consider another example of multiplication of rational numbers. Two rational numbers among 4 are negative and 2 are positive. When we multiply, we don't take LCM, we cancel. Already it is practiced, because fraction forms we have done already, and only the sign may be the negative as these are rational numbers. So if directly we are doing, of course, when you check the question given, check the denominator 5, first rational numbers, and the third rational numbers, numerator 15, we cancel 5 and 15, 5 ones are, 5 threes are we do. And similarly, second rational number 3 in the numerator and third rational number 16, the fourth rational number 9 in the denominator, we cancel. So the first numerator minus 4 and the third denominator 16 we cancel. So now I am showing this process. Which one I am combining, I am showing in the next step. Minus 4 by 16, that's what I do actually. I cancel 4 and 16, right? And 3 and 9, so 15 and 5. So I have written only in that form. Only the denominators are repositioned to make it very clear that we are cancelling those two. Those possible ones. So minus 1 by 4 is the result of cancelling 4 and 16, and minus 4 by 16 written in simplest form as minus 1 by 4. And 3 by 9 after cancellation written in simplest form as 1 by 3. 15 by 5 after cancellation written as 3 by 1. Similarly, minus 14 by 7 is written as minus 2 by 1. So what is cancellation? It is just writing the simplest form by dividing by same number, dividing by the maximum possible number and writing the simplest form. So it's shown in the bubble form, and then it is very clear that cancellation involves equivalence of the given numbers in the simplest form. So you observe the question given was higher order rational numbers different to be multiplied, and we wrote the simplest form to reach at the answer. That is what is cancellation. And in addition, we take LCM and write the higher equivalents before adding. So it should be noted and it should be clearly understood. Here are few mental maths problems. They are based on the operations addition and subtraction and on the concept of reciprocal and additive inverse. The first set, find, it has 4 problems, adding 8 1 by 7 to 5 4 by 7 and 12 5 by 9 minus 9 7 by 9 and 21 minus 21 by 23 and 19 minus 25 by 24. If these are answered directly using mental arithmetic, we are successfully visualizing this. After trying out once, we can however try pen paper method. The second set of problems, check if true. The first one is 8 by 9 is reciprocal of minus 1 1 by 8. We have to think in mind to convert the number given and then check, and the sign also. Second one, reciprocal of 3 1 by 3 is 0.3. Third set of sums, it is finding. 3 different sums are there. First one is find the product of minus 6 by 13 and reciprocal of 3 by 13. Next is additive inverse of 2 divided by reciprocal of 2. Next, successor of additive inverse of 3. All these can be tried mentally, and the faster you answer these, you will go stronger in your mental abilities. Simplify, there are few more questions which you have to work out. Of course, without looking to the next slide, because next slide has the method along with the answer. We can of course try these with the simpler method as we have already learnt in the first 2 sums which I showed. Yes, the solution is here.